Okay, Eric, on to you.
All right. Well, thanks. So hi, everybody. I'm Eric Keller. I'm a professor. I've been here at CU it's been a little over 10 years now. I'm in the electrical and computer engineering department with a, courtesy appointment in CS. So about half my students are, CS students and, half are ECE. Really just, we like, kind of software and writing code and doing good stuff like that. So what I'll do today, I have a presentation that gives a little sampling of, some of the things going on in the group. I've had a great, a great time working with, master students and, doing like independent studies and things like that. A couple of them I noticed are on the call right now. So I'm already working with some of you guys. So with that, let me share my screen and go ahead and get started, and feel free to interrupt me at any time. I'm not sure if I will be able to see the hands raised or anything. So Rajri, maybe if you could just call it out if anybody raises their hand.
Will do.
Excellent. All right, do the slideshow from the beginning. Excellent. All right, so if you need to contact me, there's my email address, and you could just search Google for my name, and my website will come up. And so the name of the group, we go by, Networking and Security Research, or NSR, sort of a play on Microsoft Research, the MSR, but, just to give a little overview of, kind of the topic areas that I'm interested in. So as a, kind of high level, overview of what my research has focused on is really, my mission is to make even the most complex network infrastructures dead simple to manage. And I do this through programmability. So why this matters is, it's my belief that many of the issues that we're having are people problems. So we need automation. We need holistic programmatic management where, computers can define and verify. And, network infrastructure is really, everything. And, when I talk about problems, it's both this, security challenges that we're facing, but then also, reliability and, performance and, cost effectiveness and, ease of deployment, launching new applications, really all of that stuff. So, networking, and I have these slides in my class. So if you're in my class, you'll see a couple of these at least. And sometimes networking is an underappreciated kind of field, because it's not as kind of sexy as machine learning and AI, but it's really that plumbing. But let me get to why I think it's actually more exciting than you might think. So networking perceived versus our research. So when you think about networking, if you're a practitioner out in the field, how do they go about learning about networking? And it's really about, certification courses on, how to configure specific pieces of equipment. There's Cisco certification, all kinds, every single company now has that, or, just on the job training, throw you out a problem and, figure it out, look through some documentation. So that's one view of networking is, and a lot of that is, kind of keeping the lights on, making sure, anytime anything goes down, troubleshooting it, and, definitely an important part of the world. And then in terms of how colleges teach networking, well, it's really around, the OSI layers and sockets programming, so the OSI layers, you got kind of the Ethernet, IP layer, TCP, HTTP. And then you typically have to, in a network systems class, have to write some sockets programs where you write a server program and a client process. But what I'm here to kind of convey is networking is a lot more than that. So it's if we were to break down what my group does, it's really exploring the computer systems issues in enabling programmability of traditionally non-programmable systems. So in programmability, means like adding APIs and much greater control beyond what Cisco gives you. In, we're talking cloud computing, it's programmability, like being able to build on-demand infrastructure, kind of out of thin air. So it's enabling that programmability and leveraging that programmability for a secure, reliable, efficient, easy to manage network infrastructure. So if any of that sounds interesting, cool, let's talk. So, networks are everywhere, and the systems behind them are actually quite complex. So, everybody knows about, the internet, but, have you actually looked into, all the nuanced stuff that actually kind of makes that work? Data centers turning out to be effectively the new computer, with 500,000 servers in a building, running really, kind of crazy workloads. Virtual or container infrastructure, data infrastructure, so just the kind of ability to move data around and process it and store it, and kind of share it. A lot of that is, all network enabled and embedded infrastructure. And if you think about it, there's really kind of three main pillars of, kind of computing. It's, the compute part, the storage part, and the network part. And really all three of them have to work together, to make, an effective infrastructure and an application. And it works at all layers of the computing stack. So every single thing about networking is not just network protocols. The network systems behind it, there's kind of research going on at the hardware level, at the virtualization level, at the operating system level, at the application software or distributed software, or at the management level. So all layers of the computing stack are kind of affecting the network systems, and that's why it's really kind of there really is a place, depending, it doesn't matter what your interests are, there's definitely something that could be done. So as a kind of overview of so the pictures are all the PhD students, the current ones. So if you've seen them kind of floating around, say hi. I won't read off the names. And then I have 4 students right now, working on independent studies, so master's students. List the names here, and I'll get into what their projects are in a little bit, but just wanted to give a little flavor of the team. So another slide I kind of talked to my classes, just want to convey this because I thought it's an important idea, is that research, if you're, no matter what topic you're going to, keep this in mind, that research is really iterative. There's not just, here we have this magic idea, it's highly novel, go build it. But really it starts with, kind of a vague idea. And it's difficult to fully see the novelty yet. There's a lot of, excellent research that has gone on, for the past, 50 years, 100 years, whatever. And, there's a lot of people doing really interesting things. So it's unclear with any idea that anybody has really what's fully novel yet. And so, you have to go out there and do something. You have to, either experiment on something or, read about something and, look into it a little further and discuss it, discuss it with your peers, with the, your advisors, and see, all right, you get more ideas on how to refine that idea. And sometimes, you get to the point and say, nope, there's nothing here, or, it's been done. And you go back, back to the drawing board, or you keep refining the idea. And so just wanted to convey that is, at least this is how I work, is, a lot of times with, independent studies, it's, kind of does sometimes feel a little aimless at first, but that's because, you know, it's a process to really, you know, get to something special and novel. So to get a little sample of, you know, kind of what the group does, I picked out 3 projects that, you know, have some possible, you know, directions, but these are ongoing projects that are active with PhD students. So the first one we call transparent network acceleration. So you may or may not know, but software-based packet processing is being widely adopted. So historically, you know, like ASICs that go into like, you know, a Cisco device or whatever is the, you know, traditional way to process network traffic. But with things like, you know, 5G or, you know, virtualization and, you know, in cloud, or even, you know, AT&T's, you know, kind of whole network and something called network function virtualization, software-based packet processing is being widely adopted. At the same time, you know, Linux has a wide ecosystem of network functionality, both in terms of the kernel capabilities and the, you know, the network stack that it, you know, just comes with out of the box, or, you know, the command line tools like, you know, IP tables and IP route and, you know, all that kind of stuff, or even the ecosystem beyond that, like, you know, software that kind of leverages the Linux APIs. So you could build a lot with Linux and you can extend it and all that kind of stuff, but it's pretty slow. It's been measured, you know, quite a bit. At the, you know, on the flip side, you know, so that has led to, you know, the academic community to really create these alternate pipelines, you know, packet processing pipelines, where, you know, this is creating completely custom processing, you know, network stacks. But it really requires re-implementing everything just to get that kind of performance benefit. And one of the kind of, you know, kind of popular libraries around, you know, that's leveraged in this is something called DPDK for the Data Plane Development Kit. And that's out of Intel. Intel introduced that. So what we're doing with TNA, or Transparent Network Acceleration, is we're really reimagining the Linux networking stack. There's kind of 2 main, you know, pieces to this. One is decomposing the Linux network functionality into a fast path and a slow path functionality. So one of the problems of why Linux is so slow is it's this general purpose thing that handles really any protocol and has to, you know, check all of that. And so, you know, up front, it does, you know, parsing of the packet and filling in data structures. And, you know, it's just this kind of really bloated case. And all of it is like these, you know, corner cases, you know, that it has to handle. And so it's doing all these checks along the way. So what we're doing is we're saying, cool, let's actually, you know, purposely, or, you know, with intent, decompose that functionality into a fast path and a slow path. So we'll consider Linux as it exists today as the slow path, and, you know, we're creating these little modules that can serve as fast path functionality, and that, you know, as long as it has a custom, you know, execution environment, you know, for it to be able to kind of execute it. Then the second part of that is, now we only want to instantiate what actually is being used, rather than this, you know, kind of code, you know, kind of the long, you know, bottleneck paths, or, you know, critical paths being through all of Linux. Well, let's just, you know, make it really thin, lightweight, and automatically instantiate only, you know, the part of the network stack that's used. So we have an agent that's introspecting the Linux kernel, and, you know, so it's monitoring it, and then, you know, as things get created. So for example, if you configure a firewall rule, so now our agent says, all right, now I know you're using kind of that functionality. I will assemble a fast path and just for that functionality, and then I'll instantiate it in what's great is Linux actually has an execution environment that could serve this purpose of a fast path execution, and it's something called XDP for the the extensible data plane, or express data path, sorry. So we can instantiate that. So this is really cool, exciting to rethink how Linux is built without it actually being too disruptive to the code base. And so some example projects in this space, one might be if you're really interested in kind of hardware and FPGAs and kind of want to get there, is something like hardware offload. So instead of just being able to instantiate this fast path inside of the Linux kernel, well, we can actually a lot of the network cards, especially in like data centers, are built with like FPGAs on them, which are just programmable ASIC. So I can define a custom circuit at runtime for on these devices. And so kind of compiling those fast path modules to an FPGA, we've already started this. There was a student that worked on it last semester, got some really interesting, exciting and, kind of results that if we take it, further, it's really, really excellent opportunity. Another is if you're more interested in, say an application. So if you're familiar with video conferencing software, there's something called selective forwarding units. And so, like if you used, some video conferencing is like peer-to-peer. So like that's how Skype was, built. I don't know if it's still that way, but that was its origins, where it would, directly connect, a source, two parties directly. With the video conferencing, more like Zoom or Google Meets, all of the traffic actually goes through a central server inside of Google or Zoom's infrastructure, and what they're running is the selective forwarding unit. And so this is what forwards different traffic and maybe potentially downsampling. So for example, if you're on a mobile device, it'll send you a lower bit stream, bit rate than somebody on their desktop with good network connectivity. And so these are actually great opportunities. We look through the architecture, and it naturally matches the design patterns that you would find in the transparent network acceleration work. So take one of these open source packages, for, SFUs, kind of decompose it, the fast path and the slow path, and go from there. So that's one project. A second project to talk about is something we're calling GHOST. So the GHOST is an acronym for 5G hidden operations through securing traffic. So underlined the GHOST part of it because it's not exactly readily obvious kind of what the acronym is, but the idea here is to be able to ensure secure and anonymous communication over an untrusted infrastructure. And so the motivation for this, and for example, is like in a military use case. So military has deployment all over the world, and they don't want to be necessarily want to have to deploy a global 5G infrastructure, but want to be able to use it because there's been many 5G networks deployed by different companies all over the place. And so rather than building kind of custom military networks, can we leverage the existing 5G infrastructure for this? Now, of course, these are untrusted infrastructures and possibly, potentially hostile to the US. And so that's where, we need to be able to kind of secure and, make the traffic anonymous. So they, if you have access to this 5G, infrastructure, if you're the country, that's hostile to the US, but it's, running that, you can't necessarily tell what the US military is doing. So that's one example kind of motivation for this. So kind of what the technology behind this would be is, what we're looking at is prohibiting traffic analysis through, two mechanisms. So the use of software-defined credentials and, anonymization techniques to obfuscate, communications, connections. And what's interesting is doing this leveraging secure hardware, while at the same time needing it to be, kind of fast and efficient packet processing. So this kind of gives a little, identify the dynamically scrambled, across the identities, inject, false locations and patterns of movement, use like onion routing, which, like, if you're familiar with Tor, that's one of the kind of techniques behind that, and false traffic to weaken analysis, even if you have access to the traffic, and then add in, kind of cover traffic, so that you can't kind of pick out anything. So doing all this on, like, mobile devices and things like that is the technology kind of we're working on. And I realize I'm going pretty fast, so we might end early, but I guess that's all right. So example projects here help implement, the packet processing to obfuscate the traffic. If you're interested in kind of learning how, kind of those types of, mixed nets might work, if you're interested in, kind of how to do that at a high rate, how to do that inside of, secure hardware, that would be the kind of a sample of a project. Another would be, ideally, so there's different kind of secure hardware. And so if you've heard of like Intel SGX or Trust Zone from ARM, and there's others, they all have similar functionality, but, it would be really interesting to be able to kind of create a library on top of it such that you don't target anyone in particular, but depending on what, the device is, it just, kind of the code, for example, the code that we would write for this application, ideally could target one of these libraries and, just work on any device. So that would be an example project that somebody could get involved with. All right. The third project that's ongoing, for lack of a better name, we're calling it BGP Chain. So, as I mentioned, the internet, it's the center of our lives. We're all communicating right now over the internet, but the core protocol behind it, which is something called BGP, or Border Gateway Protocol, is insecure. So just as a quick overview of what BGP is. So because the internet has to reach, the whole world, there's no single company that has physical infrastructure that can, connect every, kind of individual to every other individual. And so what it has to be is a bunch of different network providers. So we have AT&T, we have Verizon, we have Comcast, we have Sprint, all level 3, or whatever they're called now. So level 3, all of these networks, and they all connect to each other. And BGP is the protocol where they say, here's what I know how to reach if you come through me, and they exchange all that information, and it's what makes the internet work. But there's something called an prefix, like an IP prefix hijack, and so that's where, because there's no security, anybody that has access to, a connection, one of these connections can announce like, hey, I'm actually the owner of, this IP address, start sending traffic to me. And, the routers next to them will all say, oh, cool, that's a pretty short path. Let me send it to you. That's great to know. Thanks. But then what they do with that is they'll either inspect it, they'll drop it, and they just cause the, denial of service, against people. And what we're reading about in the class right now is, impacting, the Bitcoin network, impacting, Tor network, can all be done through BGP hijacks. And so there are attempts to fix this, and it's something called RPKI. And it's basically, if, as routers, there's this big database that's, kind of maintained by a central authority that, it was basically signing, who owns what prefixes. And, you, as a router, as a network provider, you can download this database. And then whenever you get, an announcement, you can check against this database and say, oh, is this, legitimate? The origin of this, is that correct? So that's it's great that there's this attempt, but first problem with it is it's centralized. And so that makes it, the internet is one of the greatest decentralized, distributed systems, most successful, to ever exist. And, here we're going to kind of force it really into becoming a centralized model. So it just, kind of philosophically doesn't match. And this makes it ripe for, kind of, an abuse, whether, you just attack that central authority or compel, kind of through the government, things like that. The second part is it doesn't really work. There's just the last month, saw several of these attacks, and you look through the network operators user group, their emails, and they're like, yeah, the RPKI was deployed, but didn't actually help in those cases. And the big problem is there's little or no incentive to deploy. It's really just an altruistic thing, like for the good of the internet, we should do this, but it's actually complex. So even 10 years later, we're still at less than 30% deployments. So what we're doing is, in that time, blockchain has really emerged as a viable technology. It's introduced, kind of, well, Bitcoin, kind of introduced the, concept of blockchain, whether it's probably been before that, but, started getting it popular. Ethereum, introduced, kind of these smart contracts or ability to kind of put code behind it. There's been a lot of work, such as like the Avalanche network that has made these like super fast. And so, it's an interesting new technology that, the kind of academic community has proposed might be a interesting solution, as a database of IP ownership and paths. And so we're exploring that. And so, it's decentralized, so it matches the internet. It can, smart contracts can, do the same stuff that RPKI does and more. So, RPKI doesn't do path validation, and it really helps with partial deployment. And what we're really looking at as well is how they can, these smart contracts can solve internal network management challenges. So if we can make it such that it benefits you as a network operator, even, disregarding any of the security benefits, just you get benefits and being able to troubleshoot your network, it's going to be a win. Now, it doesn't guarantee success or anything, but it's definitely, I think, worth going kind of through. All right, what would it take to really do this? And so, we're building out the systems and all that. There's an interesting project, example project that has emerged is a system to emulate the internet. So the internet is composed of, I think 65,000 autonomous systems or independent networks. And, really nobody, you kind of study, like you look through the RPKI, they, it was more of a theoretical model. But nobody has like took the entire internet and said, can we actually run a bunch of routers with these new, security measures or whatever, and measure, the actual security benefits. And so we did a, kind of little bit of evaluation of, the scalability of, container networks. And, in my estimate, we can emulate the internet run it for an hour on top of Google Kubernetes engine for about $1,000. And I think that would be something that, hasn't been done before, but requires a lot of interesting challenges to kind of push, Kubernetes scalability to its limits, because it's really focused on, kind of custom networks and things like that. So that's a really cool project that has beyond just the BGP aspect of it, but just a challenge to Kubernetes. And then another, as I mentioned, that smart contracts for network management applications would be another great use of this to really prove that this has benefits beyond just security. All right, so those are 3 ongoing projects with PhD students. I want to mention, I've also started a company called Stateless. You might have seen it. It's a spinoff of research from CU with one of my PhD students, Murad, who is now graduated. He's running the company. He's the CEO. We've grown to about 25 employees, have about 20 million in venture funding, and but having some deployments in some large data centers and network operators. And this really kind of talks about our lineage. We had started at CU, published a paper at NSDI, went through an innovation program called the NSF I-Core. Got an angel investor. There's Kamalish. We didn't even have a company, formed. We just met with him. He's like, I want to invest. I was like, cool. I don't even know how to accept your check because we don't even have a company yet. But he believed in us, was excited about it. We then kind of joined Techstars. That was a great experience. We got some NSF funding through the SBIR program, and then a couple of our kind of large investor, Drive Capital, and then the local Foundry Group. So why I mentioned that is what I actually get to see as part of this is a lot of kind of real challenges that exist out in industry. And why I say Stateless Inspired is there's some problems that Stateless is solving because it directly impacts our business, but these kind of peripheral things that we're not touching, and they could be good projects. And so one example, again, come back to hardware offload, but this one is different. So in that DBDK library, they actually have something called RTE flow, and it's really this API to be able to offload to network cards or switches. And this hasn't really been exploited in industry, and not what I've at least not that I've seen. But because so much packet processing has moved into software, if we could then take that and say, cool, that's the ground truth of processing, all the capabilities that you need, but here's a couple of flows that need to be faster, or elephant flows that really take up a lot of bandwidth. Let's take those, offload them into hardware. And so there would be an interesting project to explore those capabilities. A second is make RAM Cloud open source. So I'll caveat that and say it's already open source, but let me tell you what RAM Cloud is. So RAM is an in-memory key value store, came out of Stanford. And it was designed really for these high performance computing. So really, leverages like RDMA and, every single technique to make things super fast. And it blows anything else out there out of the water. It's just really fast. And so we use it at Stateless. But, Stanford has effectively been an academic project. I wouldn't say abandon it, but they don't maintain it. The students have graduated, moved on, and that's great. And it's Stateless. We have all the engineers, that know how to use it and deploy it. But I think there's a great opportunity to really put some open source momentum behind it, make it much easier to deploy and use. And part of that might be to leverage some, what I mentioned earlier, XDP, that Linux technology. Have an improved client library. So Stateless has done some stuff that to make it much more usable, but kind of making that more widely available, and put effort around the usability and things like that. So there's a lot of possibilities here. If you're interested in like database systems, this is one that's particularly well designed, and could have an interesting opportunity there. And then the last, one listed here is explore different. So cloud networking, if you look out there, it's, kind of it's a hot topic right now. And there's a model, because basically using the cloud is hard. Connecting up to your, own infrastructure is hard. Connecting it between, Microsoft and Google and, Amazon is hard. And so, there's been companies like Aviatrix is kind of the premier one. They introduced a model, which I labeled it as an overlay. So how it works is in every single one of your VPCs that you launch in, any of your cloud infrastructure, you run one of their virtual machines. So now, of course, you're paying for it, both paying to Aviatrix, but then also paying to like Amazon to run this virtual machine. But then it gives you this ability to, see a simple management of like putting in network, policies of like, this collection of, this application can talk to this application, but it cannot talk to this application. So those are the kinds of things that it provides. And it builds an overlay, meaning it's, effectively over the internet, between, it creates like tunnels between these virtual machines. So that's the current model. I think there's an opportunity for a cloud-based service provider model. And so if you think about, something like, you go get network service from Verizon, it's not Verizon, putting all, not running any gear or network and just saying, here, we'll put something in your infrastructure and then use the internet. Well, no, Verizon's maintaining, that and then allowing people to connect to it. And so there's an interesting opportunity here to explore, the benefits, and cost effectiveness, because with that model, now Verizon, can multiplex, across a bunch of different customers. So make it much more cost effective. They can continually, have, network management techniques to, seamlessly perform updates, whereas it's disruptive to kind of use stuff like, launch a VM inside of your, infrastructure. So those are some example projects. The current independent studies, the list here, one is looking at RDMA in serverless frameworks. So RDMA is for remote data memory access. So DMA is like allowing your network card to talk to memory without going through the processor. And remote allows, kind of two network cards to effectively do that without involving the processor. So this is one of the techniques to get really low latency, communication. Another is looking at how to leverage or kind of restructure serverless frameworks for machine learning. Oh, so I guess if I didn't mention what serverless is. So the concept is, and where the word serverless comes in, is you don't have to worry about any server infrastructure. You as a designer say, here's a function that I want to execute whenever I get, for example, an HTTP request. And then you give that to like one of these frameworks. The cloud providers, have their own frameworks. And as those requests come in, they'll make sure that it's running. If more requests are coming in than that particular instance can handle, they'll automatically scale out and things like that. So it makes it really simple to create applications and manage it. And the flip side would be you kind of yourself launch a virtual machine or a container that decomposes the application in a particular way. So these are a couple of projects kind of looking at different aspects of serverless. Looking at the transparent network acceleration, the TNA project, looking at the Kubernetes networking. So a lot of it just uses Linux networking. Some of these network plugins, like Calico, is just using Linux networking. So we're exploring, kind of how to, the effectiveness and, what are we missing and things like that. So that's one of the projects. And then the last one, cost optimization among various, cloud deployment models. So, taking different workloads and saying, well, if you were to implement it in serverless in this particular, frameworks model versus in this serverless frameworks model versus, in containers or, VMs, what are the, different implications for each of those? So those are some, kind of pretty exciting projects going on. And that's all I got. So with that, thanks to everybody, and, happy to take any questions or, yeah.
Thank you, Eric. Oh, we
Yep.
have Chetan raised hand. Chetan, you want to go?
Hey, I had a question about you talked about DPDK using DPDK RT flow to offload something to the hardware. So what exactly is being offloaded?
So as an example, so in software, let's say you're doing NATing, and it's a dynamic NAT. So NAT is a network address translation. Translates, it's something like, for example, are you familiar with NAT?
Yeah, I mean at a high level, yeah.
Okay. So whenever, so it's, for example, inside of your, home network, how you have, like, say 5 devices. Maybe you have, a Fire Stick on your TV, you have your phone, you have your laptop, but, they don't each have their own public IP address. They have a private IP address. And so why that is because at your, home router, it's doing NAT. It's translating those, TCP ports and IP addresses, private IP addresses, into, say, the one IP address that Comcast or CenturyLink gives you, if those are your provider. And so that's a process that's dynamic, that it selects from a pool of addresses, as it happens. So that doesn't really work well for hardware when you have kind of these dynamic, decision making and things like that. Let's say that's in software though. Linux does this, pretty easily. But now I still have to go through software, to look at up in that table. So what would be kind of useful is I can take that flow entry, that, for whatever decision it made, take that, write it down into hardware, and such that all the processing, there's no dynamic, it's just looking up in a table and sending it out. And now I can do that at hardware speeds. So that's one example of, like a simple example like NAT, but really any functionality, IP forwarding, packet filtering, IPsec, all of those, kind of are, have those dynamic parts, but then once it becomes a static decision process, well, let's offload it to hardware. So did that answer your question?
Yeah, got it. So you don't need any smart NIC kind of capabilities as such.
It depends on the extent to which you want to, kind of offload. And so the more capabilities your network card has, the kind of better, the wider range of capabilities you could offload. So yeah, I would have in mind a smart NIC or, like a switch.
Okay. I also had another question about so the transparent network acceleration. So do you use eBPF programs to filter out certain packets that you're interested in and pass that to the XDP to whatever user application should get that packet? Like, does it how?
Yeah.
Like, do you?
So the great question. So XDP. So stepping back, eBPF, since you mentioned that. So eBPF is a technology that was introduced into Linux, a while ago, maybe 15 years ago. And it's really hooks into various, and it's not just a networking technology, but it allows you to write code. So in Linux, you can write kernel modules in C, get those loaded into the Linux kernel. The problem with that is it's not necessarily safe. You can have infinite loops, you can have null pointer exceptions, you can have, things that crash the kernel. So what eBPF did was basically introduced, a language or, kind of a bytecode that's gets sandboxed and, kind of verified before it executes inside of the kernel. So it's safe execution of custom, kernel processing, and that has various hooks into it. So that's eBPF. XDP, all it is it introduced hooks into the Linux networking stack. So it relies on eBPF as the kind of the mechanism for you to write that custom programs, and XDP is just the kind of the hooks into the Linux part of that. And so do we use eBPF to filter out traffic? Yes. That's how you decide kind of what traffic should go, through this fast path versus, what should go through, kind of the Linux networking stack, the slow path.
So the fast path bypasses the kernel stack.
I'm sorry, can you say that again?
Does the fast path bypass the kernel stack?
The fast path, yes, would bypass the kernel stack. So that's why
Okay.
it's fast.
So this is something that you do in SFUs as well. So you mentioned about SFUs.
SFUs today do not do this, but we think that there is a really strong opportunity to do that.
Okay. How is this better than DPDK in terms of throughput and stuff?
So DPDK is going to be, it's been measured to be slightly faster, but we're talking less than 5% faster in terms of throughput. DPDK, the way it handled, the safety in the kernel was by doing everything in user space and then introducing techniques, like zero copy and, for ways to get network traffic off of the network card into user space. But this would fall into this example of, once you start working with DPDK, you're re-implementing everything. You want IP forwarding, well, you have to re-implement, that code, the way to write the forwarding tables, all that stuff. If you're using XDP, being that it's in the Linux kernel, there's actually, ability to read from the Linux forwarding table as part of your, kind of processing. So it's more deployable is why this is better than DPDK. But that said, I'm a big fan of DPDK, and it definitely has its place.
Okay. I think DPDK needs hardware support as well, right?
Not really. It needs,
Okay.
a driver,
Mhm.
to be able to do this. So it needs, just like, and so that's another benefit that you mentioned, like Linux has a lot of network drivers already. You need, DBDK has to re-implement, network drivers because it's, interfacing to them in a different way. Cool. Thanks for your
Okay. Yeah.
questions.
Thank you. Yeah.
Pritham,
So I want to know what would be a fast path and a slow path, like an example.
So a slow path, IP fragmentation. So Linux, handles, everything. So, well, let me actually, so we just wrote a paper. The example we used in that was a simple example of bridging. That's a Ethernet layer device or, kind of protocol. So in the slow path, one of the things that you do in Ethernet is a spanning tree protocol. And so that's to ensure that you don't have any loops. And that's kind of control plane functionality, but right now it's part of the Linux networking stack. So whenever you get an Ethernet packet, it's actually checking, does this need to be, processed as a spanning tree protocol. The bridging part is dead simple. Like if I want to connect one, network, like bridge, one network interface to another, it's really just a simple lookup table and, kind of connecting between those two interfaces. And so here, why you would want to do that in software is, there's a lot of virtual machines running or containers running or, between machines. And so bridging is, something that would be used. So that's one example where the actual bridging, the forwarding part can be a fast path. The spanning tree protocol can be the slow path. In IP forwarding, cool. IP forwarding, can be fast path. But say you kind of reach something like IP fragmentation where, the size of the packets that you're allowed to, they have to be reassembled or broken apart. Well, that's something that's not fast. That's kind of corner case. So let's send that over to the slow path in Linux. Does that make sense?
Yeah, kind of. Yeah.
Excellent. All right. Thanks for the question.
Thank you.
so we have, sorry, your name doesn't appear. It just says iPhone. So sorry about that.
Is that me that you're talking
Yeah.
about, Rusty? Oh,
Yes,
all right,
it
all right.
is.
Oh, really? Oh, well, it's Aaron. Hello.
Aaron, that's what I thought. Your face is really small and I can't even see
Well,
properly.
I'm using my phone here.
Okay, there you go. Go for it, Aaron.
Yeah, that's what it is. Yeah. Hey, thanks for all that, Dr. Keller. I just had a question. How does the guy get started researching, and what are you looking for, like, to bring people onto your team? I mean, how does that, I guess I'm asking, how does that kind of work?
So what's the process? I don't know. We chat. That seems to be how it, or you probably better you chat with my students, because then they tell the real deal, and find what they're interested in. But in general, just chat with me is really the process. And if we kind of find common interests, what I look for in students, just drive, an interest in learning, and ability to really like a systems ability, like ability to put together software packages, ideally write software, kind of, I don't want to call it, say, hacker, because that has that kind of the security version of hacker, but that kind of hacker in terms of like just being able to hack stuff together and put them together. That's a lot of what we do as kind of systems researchers, is kind of build experiments and kind of write software and have to use whatever tools are out there. So I don't know, did that help answer, or do you have a more specific question?
I'm thinking maybe I'll email you, and if you have time next week or something, maybe we talk Tuesday or Thursday, if that works for you.
Sounds good.
Cool.
Can I ask a question?
Go for it.
Yeah, thank you for your presentation. And I have it's a little bit broad, I think. So is there any network research on the IoT or embedded machine in your lab?
Is there any research on IoT or I didn't catch the
Between the machine or something? I mean, your presentation feels more like broad using the internet, the connection with some server or something. I guess, I'm not sure.
Yep.
But so I want to know about a little bit the low level or between the networking with the small device or something.
That's a great question. I would say that has not necessarily been my focus, but doesn't necessarily means it's out of scope. And what I've found to be most successful in terms of kind of researching with students is going where their passions are, because if somebody's passionate about something, they're more likely to really immerse themselves in it and become the experts and teach me something. I can help guide them and kind of point them in the right direction. But when it flips to the point where they're teaching me, that's really great. And so I typically kind of work with students in that way of really I have a broad umbrella. A lot of, like I said, it's across the whole, I have people doing FPGA stuff and then people doing like cloud infrastructure stuff, and even blockchain stuff. And, so it is broad, which is sometimes a weakness, or, but it really is under that network systems umbrella. So no, I don't have any active projects that I can think of. We have thought about like what is the implications of serverless at the edge, but haven't really dug too deeply into those. But always happy to explore, see if we can find something.
Thank you.
Yep, thanks for the question.
I think we're done with questions. I don't see any raised hands unless I think that's the old hand. So once again, thanks, Eric, for your time and the presentation. I'll be posting this recording on the sheet and the website. Students know where to reach out for the video. Thank you once again.
All right, well, thanks for having me. And thanks everybody for listening. All right, and I look forward to chatting with anybody that wants to follow up.
Great, thanks.
All right.
Bye.